Hello everyone. My name is Reed, and since the 5th grade, I've suffered from anaphylactic allergies, specifically to tree nuts. What that means is when I ingest tree nuts, my throat begins to swell, I have trouble breathing, and I can easily die in a few minutes if I don't receive the proper dose of epinephrine. This has happened to me twice in my life. The first time, I was in my own home and had epinephrine readily available. The second time, I was at the gym, about halfway done with a protein shake when a friend looked at me and said, "Hey, Reed, what's going on with your face?" It took me a second to realize what he meant by that, and that I didn't have my auto-injector with me. Luckily, I was in my hometown and knew the ER was just across the street. I drove myself there in 4 minutes. Some people aren't fortunate to be next to the ER when they need it most. For Ishmael Ashraf, who was just 9 years old at school, when he looked his teachers in the eyes and said, "I think I'm going to die," as they frantically looked around the room for his EpiPen. It took 11 minutes to find it. 11 minutes was too long. In a study taken by the National Allergy Association, they found that 60% of high-risk patients didn't carry their auto-injectors regularly. And out of the 40% who did, half of them were carrying expired epinephrine. That leaves 80% of the anaphylactic community at extremely high risk. But it's not just kids, it's students, it's adults and teens as well. Dylan Hill, who was just 18 years old when he actively chose not to carry his EpiPen to dinner one night, as he didn't like the look and discomfort of carrying it in his skinny jeans. He didn't have his auto-injector when he needed it most. If one of the previous stories didn't startle you, I hope one of the following statistics does. 1 in 50 Americans has anaphylactic allergies. 1 in 13 children suffers from allergies, and every 3 minutes someone goes to the hospital for this exact reason. Now, the number of children with anaphylactic allergies in the United States has been growing at a staggering pace. From 1997 to 2011, it increased by 50%, and it's continued to climb since. This is a serious problem, and the devastating truth is we lose lives to this disease every single year. I'm now going to hand it over to Alex, who will introduce you to some of our solutions.
Thanks, Reed. We started last fall by sending out a survey to 90 different auto-injector users to try to get a better understanding of our user base. They helped us identify 2 key metrics to use in evaluating potential solutions. These are the portability of the device and the burden that it places on the user in having to remember it on a daily basis. We then evaluated the existing solutions, with the EpiPen scoring particularly poorly by both of these metrics. There has been improvement in the recent years with the introduction of the AviQ into the marketplace, but we think there is room for further improvement. We then explored further into the design space, eventually settling on the watch profile. This design has allowed us to create a more passive relationship between the patient and their auto-injector. The next step was to identify the key metrics we were going to use when creating this device. These are broken down into 3 categories, which are the medical, the user experience, and the reliability of the system. This has allowed us to create a device that is safe, comfortable, and robust. And now I'm going to hand it over to Ben, who's going to talk about our solution, the LifeWatch.
Thanks, Alex. LifeWatch is the first wearable epinephrine auto-injector for people with anaphylactic allergies. Jake has a device on his wrist right now without a needle, and he's going to show you just how it works. If a user needs to perform an injection, the first thing that they do is they take off the back safety cap. Next, they pull the device out of the outer case, and then they push it into their outer thigh. This triggers the injection. Afterwards, they can cover the needle with this revolve lock that locks in front of the needle and protects the user. Let's take a look inside. The device has 5 main components. The first is the main body, which houses all of the other parts. Next is the syringe, which has the needle that gets driven into the user's thigh, as well as the medicine that's administered. After that is the activation button, which is pushed against the user's thigh and triggers the activation sequence. The needle shield, like I just said, covers the needle and shields the user after injection. And finally, the safety case holds the device on the user's wrist and protects it from potential damage. Let's see all of these parts working together. First, the safety cap is removed and the device is pulled out of the case. Next, it's pushed against the outer thigh, which drives the activation button up. This releases 2 flexures and pushes them to the side, which allows the syringe to be driven down by 2 springs. This action further pulls a pin, which releases the plunger and pushes fluid out of the syringe. After the injection is complete, the needle cover is rotated over the needle to protect the user. We took a fairly iterative design approach with this device, and we'd like to share some of the decisions that we made along the way. One of the first things that we did was perform injection tests on human flesh analogs. We did this to find the required force to push a needle into the user's thigh, as well as the required fluid pressure to push fluid out of the syringe. And the values we got from these tests matched that of the literature. Next, we wanted to confirm that the fluid flow profile through our custom syringe and needle geometry would match that of an EpiPen. To do this, we researched the EpiPen and found the outlet velocity of an EpiPen and compared that to a computational analysis of our device. And we found that the two outlet velocities were roughly the same. When we began prototyping this device, we started using extension springs, but as you can see, those hooks on the end on the left side take up a lot of room in our very small device. So we switched to compression springs, which gave us more room in both activation and injection. But which springs to choose? We surveyed the options that were available on the market and plotted them on this force versus displacement graph. For activation, we need springs with very high deflection, and for injection, we need springs with low deflection but very high force. That limited us to the two regions that you can see here, and from there we were able to down select even further based on other parameters such as the outer diameter of the spring. For activation, we developed this flexure system whereby the activation button pushes up and deflects two flexures to the side and gives room for the syringe to be driven down. After testing, we realized we had to increase the contact area of the activation button on the bottom in order to ensure robustness and reliability. Then, to make sure that this flexure system worked every single time, we wanted to perform a stress analysis using FEA on the system. We did that with the nominal spring force and found that there was significantly lower than the yield strength, meaning that this would work. I'll now pass it off to Daniel. We'll talk some more about some of the other components.
Thanks, Ben. We spent a lot of time thinking about the user experience of our device. We started with an open-faced bottom, but that proved to be impractical for sterility concerns. So we transitioned to this closed-faced bottom with a buccal interface. And over a series of iterations, we've come to the final design that's extremely easy to use and interfaces directly with the safety caps, reducing our part count. One of the hardest parts of the design was developing a fluid quick-release mechanism that was both small and strong. In the initial locked configuration, material interference holds everything together as shown in the middle. Once the center pin is pulled, the spheres become unconstrained, allowing the springs to push the plunger out. These springs act through a complex force chain, which is resolved as an effective frictional force keeping the pin in place. That's opposed by a string pulling up on the pin, and by analyzing this force system, we can optimize the taper angle theta. By changing the materials involved, we can reduce the resistive coefficients, and by changing all of the various geometric constraints, we can set a nominal required pull force that is well within available bounds, even accounting for standard manufacturing tolerances, indicating that we can pull the pin every single time. But we also need to seal the fluid chamber itself. We started with a flat piece of rubber, which we thought would be a simple solution to this problem, until we started testing it. We realized that we need to look at industrial-grade syringe geometry, material overlap, and material hardness constraints, allowing us to have our custom seal be almost 100% effective. And as a medical device, this needs to be completely safe. So before injection, the safety cap locks the activation flexures in place, preventing anything from moving. And after injection, the revolve sheath locks into place with a keyed slot mechanism, preventing any accidental needle pricks. But does the device actually work? So we looked at two main metrics directly from EpiPen literature: the fluid dosage volume and the standard deviation. What this graph shows is that with plunger A, over a series of 50 trials, we were able to hit a standard deviation that was at or better than the EpiPen itself. However, the volume was a little bit low. So to combat that issue, we improved our manufacturing method with plunger B. That allowed us to increase the volume towards the target value without negatively affecting the standard deviation at all. This shows that with commercial manufacturing processes, we should be able to hit that target value. To validate the fluid flow analysis, we took a slow motion video of the full system working, extracting the distance and the time to get an outlet velocity that matched almost exactly the expected values. And as we've said again and again, the small volume of our device is one of the primary design metrics. What this slide shows is that the final volume is less than half that of the EpiPen and almost half that of AviQ, which is the smallest available market option today. Finally, as a user device, we need to make sure nothing bad happens if it's dropped or smacked on a table. So we conducted a series of 1 meter drop tests, both with and without the safety case, looking to make sure there were no early activations and no failures to activate after being dropped. With the safety cases on, we saw a 100% success rate. Without the safety cases on, we saw similar results on all of the relevant faces, although we do see some early activations when dropped on the side without the case. This leaves us some room to improve, which we could do by stiffening the activation flexures themselves. In summary, we hit almost every single metric we set out to, including all of the user experience and reliability metrics, and most of the medical metrics. The remaining medical metrics we showed high design feasibility for. We'd like to give a huge thank you to the teaching staff and advisors and our funding sources who have really supported us through this whole journey. We have developed a smaller, more easily rememberable device that will enable us to help save lives every single day. At this point, Spencer is going to hand out a needleless version of our device as well as an EpiPen trainer, so you can really get a feel for these systems. Thank you, and we're now open to questions. It's a good question. If you want to give the appendix slide.
Yeah.
So we did some pretty detailed manufacturing cost estimates looking at materials involved and the process to make them. Most of these things could be injection molded, which has pretty low scale costs at high volume. So the estimated manufacturing cost per device is around $10. For reference, the EpiPen is bought for around $35 each from an external manufacturer. So, I mean, there's obviously room, you have FDA regulations, but
Yeah.
right.
Yeah, correct.
Yes. Right.
There's a very complicated supply chain and economic chain that could be an entire presentation on itself. But yeah, a lot of that is not going into actually developing the device.
What do you think these could sell? So right now, the EpiPen is sold for $304 per device, and the AviQ is sold for $4,000. So those are, again, not necessarily, they're due to some complex supply chain. So we are planning to sell ours for roughly $100. So that would be the price for usual copay, thus allowing someone to pay for the device out of pocket if they weren't insured.
Once it's used, can it be used again? I mean, can you refill the vaccine or the?
So
Generally, the products on the market aren't reusable, and so we're trying to aim for something similar.
So as it's a device that's used, like injected into your body, we theoretically could make it reusable, but we don't want to give the user that burden of having to make sure they put it back together correctly. So if they sent it back to us, we could maybe reuse some of the parts. Nothing actually breaks in it, but it's comparable to the similar products where the EpiPen you use once and you throw in the garbage.
The other concern with that is sterility. So because the needle goes into your thigh and it becomes, dirty potentially, we don't want to reuse that unless we have a very strict cleaning process, at which point it might make sense to just get a new one.
Even if you're injecting on yourself, you still have bacterial and viral concerns from stuff like that.
Another question is, if the EpiPen expires in like a year or so, will that also happen here?
Yeah, so that's a function of the actual epinephrine inside. So we're not messing with the drug itself. Where it's really a mechanism and delivery redesign that we've worked on. And so that's kind of beyond our control. There are other companies working on developing other formulations that we could potentially look to partner with that would have a longer shelf life, but that's just a function of the actual epinephrine.
Yeah.
So going back to one of the early presentations with the opioid epidemic, there was talk of having Narcan everywhere for this.
Yep.
Besides Narcan, which could be another use of this, do you see other uses?
Yeah, so that's actually something, a great point, we've looked into. For naloxone, they're trying to get people to have these smaller versions. It's kind of like AviQ, they actually make it, the same company, Kaleo, that owns AviQ, makes an auto-injector for naloxone, which is used to treat opioid overdose. So we're looking into potentially using other drugs for any injection that's similar to this.
And more specifically, the dosage volume for epinephrine is 0.3 milliliters. For naloxone, it's 0.4 milliliters. So it wouldn't even need to really change the profile of the device at all. So it's definitely an area that we're looking into actively.
Correct.
What does the market look like for this device? Is it patentable?
Yeah, that's a great question. And the market for this is heavily reliant on IP. We've gotten a provisional patent on this device already, but the device is very different internally from the vast majority of other things on the market, and it's also very different compared to how other devices compare to each other. So we don't foresee any specific problems. We're not patent attorneys, so maybe we should talk to someone a little bit more knowledgeable, but
We're in the process of a patent search with a patent attorney right now.